So far, we've covered how the first three kinematic equations were created. The first formula was created by finding the area underneath the VT graph, the second formula by its slope, and the third formula was an offspring of the first two. So how do we create another two more equations? Simple, by rearranging equation number 2 before substituting it in. Let's say we decided to rearrange equation number 2 by bringing the a delta t term over. That term will become negative after we clean the equation up. We then substitute the rearranged equation 2 into equation 1. Collect like terms, then expand and simplify. And that's how we get to equation number 5. At least equation number 5 according to your textbook. Equation number 4 is a bit more challenging to prove. We start off with equations 1 and 2, but this time we isolate equation 2 for delta t. You'll notice that when we substitute equation 2c in, we end up with two binomials in the numerator. If you recall from math class, when you have two binomials and you need to expand, you need to use the FOIL method to expand this type of expression. After you've expanded, two terms will subtract each other out, and you're left with this less messy looking equation. This equation is mathematically correct. However, physics textbooks like to show this formula rearranged for VF, so let's go and do that. We first multiply both sides by a, bring the negative vi squared over, and finish off with a quick swapperoonie. And that's it, equation number 4. Tonight's homework will utilize all 5 of these equations. Just keep in mind that each equation needs 3 givens in order to solve for the 4th variable. One more thing, there's an easier way to convert meters per second into kilometers per hour. To prove the shortcut, let's start off with the unit length of 1 meter per second. To get rid of the meters in the numerator, we need to multiply it by 1 kilometer over 1,000 meters. And to get rid of the seconds down below, we'll need to multiply everything by 60 seconds over 1 minute. Then multiply by 60 minutes over 1 hour. After canceling out most of the units, we're left with 3.6 kilometers per hour. Now logically, if 1 meter per second translates into 3.6 kilometers per hour, then 2 meters per second would be double of 3.6, which is 7.2 kilometers per hour. So anytime we need to convert from meters per second into kilometers per hour, we multiply by 3.6. And if we need to go the opposite way, then we will divide by 3.6. Here's an example of how you can incorporate the shortcut into your homework. Say in your givens, Vi is equal to 2 meters per second. If you need to convert it into kilometers per hour, then write down times 3.6, and on the next equal line, write down equals 7.2 kilometers per hour. Here's the first example of the day. Find the final speed if delta d equals 5 meters, a equals 10 meters per second squared for a duration of 4 seconds. How about you pause the video right now and see if you can get to the right answer. Did you get to the answer 21 meters per second? If you did, good job! Let's take up this problem anyways. We first start off with our givens and require. After looking up on the cheat sheet, we see that equation number 5 will help us out here. However, we'll need to do a bit of rearranging. First, we'll bring over the negative a delta t squared. Then we'll do a quick swapperoonie. With Vf delta t on the left, we divide both sides by delta t, and here's the formula rearranged. Beyond here, we substitute in our knowns, follow the rules of bedmass, and conclude with 21 meters per second. Now, if you're able to rearrange the equation in your head, and then show your first substitution before your final answer, that's perfectly fine. Just make sure that you line up your equal signs and include units in your solution, like you always should. Here's the second example. Pause the video again and see if you can get to the correct final answer. As usual, we start off with our givens and require. Looking at the table again, it looks like equation number 4 will help us out. However, to isolate for a, we first need to bring vi squared over. Divide both sides by delta d, and then finish off with a quick swapperoonie. Right after our first substitution, we might have realized that things are going to get messy here. What we should have done was to state an assumption. We'll write right above our given statement, assume forwards as positive. That way we can drop all of the vector symbols. 5 squared is 25, and 10 squared is 100. Simplifying this expression gives us negative 1.9 meters per second squared. Now if forwards is positive, then negative is backwards. One of the most challenging equations to rearrange for is isolating equation number 3 for delta t. As you can see, there are two delta t terms in the formula. One of them is linear, and the other one is quadratic. Quadratic. Well, you know what this means. First, we arrange the formula in standard form. Keep in mind that when you move delta d over, it will become a negative delta d. Next, we extract out the a, b, and c term. Here, keep in mind that a isn't just a anymore, it's now 1/2 a. Beyond here, we sub the terms into the quadratic formula as necessary, and eventually get to our answers. However, this isn't always necessary. Sometimes we can get away without using the quadratic formula. For example, with these three givens, you'll notice that one of the terms is 0. In this case, when the constant c term in the quadratic formula is 0, we can solve by factoring out the delta t. With the units removed, we have 0 equals 10 delta t minus t squared. When t is factored out, we can determine the two roots of the equation. Here's another one. This time the linear delta t is 0. With the middle term gone, it's pretty quick to isolate for delta t. We first multiply both sides by 2, divide by a, and since t is t squared, we square root both sides, and this is a much easier formula to solve. The same is true if we're trying to isolate for a instead. But this time, we multiply both sides by 2 and divide by delta t squared. Tonight's homework is to finish off course pack page 16 and try out course pack page 21. We're almost done with the unit, so the sooner that you complete the review questions, the more time you'll have to properly prepare for the unit test. Stop this video right now, and you can come back and watch the remaining unscripted video to compare your solution with mine. So first, this tells you that VF goes to 0 at a complete stop, and just to keep the units consistent, how about we convert the kilometers per hour into meters per second by first dividing by 3.6. Next, we pull out the kinematic equation. VF squared is equal to VI squared plus 2a delta d, and isolate for our a. We first bring over the VI squared, so we have VF squared minus VI squared is equal to 2a delta d, and to isolate for a, we divide both sides by delta d. After we substitute everything in, watch out for two things. First, make sure you square what is in each of the v's, not the entire numerator, but in the individual terms. And in the denominator, make sure you expand out the 2 kilometers into 2,000 meters. If all goes well, you end up getting negative 19.29 meters per second squared, where when you look at the givens, worst case scenario is 2 sig fig, so your final answer is also 2 sig fig. For question number 10, just to maintain consistency, let's convert everything into meters per second. Now, when you divide by 3.6, you're converting kilometers per hour into meters per second, so you end up getting meters per second divided by seconds. Or meters per second times the reciprocal of seconds, which is 1 over seconds, which gets you meters per second squared. So that's how the first one works out. The second one I hope is self-explanatory. Whenever you convert from kilometers per hour into meters per second, you divide by 3.6. Beyond here, you take that same equation as before, Vf squared is equal to Vi squared plus 2a delta d, but this time around, isolate for delta d. So you bring the Vi squared over and it becomes negative. And this time around, we divide both sides by 2a. Delta d is equal to Vf of 5.0 meters per second squared minus 13.889 meters per second squared, all divided by 2, negative 5.5556 meters per second squared. Of course, this is a bit overkill with the number of significant digits that we include in, because we know that our final answer is going to be 2 sig fig. We'll stick with this for now, but you can try it out later on that even if you delete out most of these, as long as you carry at least one extra significant figure compared to your final answer, you'll still get to the right answer. If all goes well, you end up getting 15.111 meters, which again is overkill since you only need 2 sig fig. So this will drop down to just 15 meters as your final answer. For question 11, it's often helpful to just draw out a sketch just so you can see what's happening with the position time graph. The car accelerates from rest, and then after a certain point, it decelerates back to 0 again. So it starts off at 0 meters per second and finishes off at 0 meters per second. The inflection point where it begins to decelerate happens at the 450 meter mark. So initially it was accelerating at positive 14 meters per second squared, and then it was decelerating at negative 7 meters per second squared. And that's about all the information that's given to you. So to figure out how far he has traveled in total, you'll need to figure out what the Vf is right over here. And with that, that will become the new Vi to figure out your final displacement. So that's what we'll figure out first. Vf squared is equal to Vi squared plus 2a delta d. Since Vi is 0, this simplifies down to 14 meters per second squared times the distance of 450 meters. Pull out our calculator, and we get 12600 meters per second, and that's meters squared per second squared because I haven't square rooted that yet. That gives you 112.250 meters per second. All right, again, that final velocity becomes the brand new initial velocity for our second segment. So for our second segment, we have a Vi of 12250, an A of negative 7 meters per second squared, and a Vf of 0 meters per second. And we're trying to isolate for delta D this time. So we're going to take the formula. When we bring the Vi over, it's going to be negative Vi is equal to 2a delta D. So delta D is equal to Vf squared minus Vi squared all over 2a. Again, if this rearranging exercise is one that you can do naturally, then by all means show your formula rearranged. But keep in mind that if you made a mistake along the way and you didn't show your work, well, there's less forgiveness I can give you when I mark your test. So Vf goes to 0 meters per second. Vi is 112.250 meters per second squared, all divided by 2, negative 7.0 meters per second squared. When you calculate through all this, you end up getting an answer of 900 meters. So it's asking the total distance of travel. So we know that our total distance of travel is equal to delta D1 plus our delta D2, where this is effectively our delta D2 over here. So our first displacement was 450 meters. We add an additional 900 meters on top, and that works out to 1350 meters. Looking at our givens, the worst case scenario is 2 sig fig. Our final answer should just work out to 1.3 kilometers. Whoops, not 1.3, 1.4 kilometers. When it's odd, you round up. It's only even when you round down. In this question here, yet again, it's easier to draw the diagram just to see what's happening. For the first 10 seconds, you don't travel very much. But between 10 and 15, you travel quite a bit more. So what you want to do is you want to figure out what your position is over here and what your position is over here, and you're looking for the difference between these two. So delta D is equal to position 2 minus position 1. Again, this starts from position 0. So when you take a look at the kinematic equation, the third one, delta D equals VI delta T plus 1/2 A delta T squared. This delta D, by definition, is equal to final position minus initial position is equal to VI delta T plus 1/2 A delta T squared. So our final position is equal to our initial position plus VI delta T plus 1/2 A delta T squared. In fact, some textbooks show this as a third kinematic equation, because it too is also correct. As we stated, initially we started at a position of 0, so that value goes to 0. Also, it starts from rest, so this term also goes to 0. So wherever you are at the end, your final position is just simply equal to 1/2 A delta T squared. So our final position for segment 1 at 10 seconds is equal to 1/2 times 6.0 meters per second squared times our 10 seconds quantity squared. 10 squared is 100. 100 times 6 is 600, so divided by 2 gives us 300 meters. So that's our first position. Keep that aside for now. Next, D2 is equal to 1/2 times 6.00 meters per second squared times 15 seconds squared. When you crunch through all this, you end up getting 675 meters, and that's position 2. So we know that position 1 is at 300 meters, and position 2 is at 675 meters, and we're just trying to look for our delta D. So our distance between 2 and 1 is simply equal to D2 minus D1, or 675 meters minus 300 meters, which gives us our 375 meters. 3 sig fig. Final answer, also 3 sig fig. (13) is kind of similar to 12, but a lot more challenging to solve. Again, as I mentioned, as time goes by, the distance you cover is going to be far greater. So this is telling us that it travels 150 meters from these two positions here. So the 5-second mark, and the next 5 seconds, which works out to 10 seconds. It travels a total of 150 meters. It starts from rest, and because this curve is quadratic, we take it that the acceleration remains uniform. So we got to figure out our acceleration first, then we can figure out the rest of the story. So how do we figure that out? Well, again, when we start off with delta D is equal to VI delta T plus 1/2 A delta T squared. Delta D has the same meaning as dF minus di is equal to VI delta T plus 1/2 A delta T squared. Or dF is equal to di plus VI delta T plus 1/2 A delta T squared. Again, this object starts from rest, starts from the same known position as position 0, so our final position is just equal to 1/2 A delta T squared. So in our first case scenario of our D1, that's equal to 1/2 of A that we don't know yet, but 5 seconds have gone by. So our D1 is equal to 1/2 A times 25 seconds squared, and we're stuck. There's equation number 1. For our second equation, D2 is equal to 1/2 A, and this time around our time 2 is equal to 10.0 seconds. D2 we don't know of. 1/2 A, 10 squared is equal to 100 seconds squared. Two equations, two unknowns. Guess what we're going to do? We're going to sub them in back into our initial definition. that between position 2 and position 1, that worked out to 150 meters of travel. So 1/2 a of 100 seconds squared minus, or I should restate the formula up here, d2 minus d1 is equal to 150 meters. Is equal to 150 meters. All right, so 100 minus 25 gives us 75 divided by 2 is 37.5 seconds squared times a is equal to 150 meters. So a is equal to 150 meters divided by 37.5 seconds squared. I believe that goes in 4 ways, so a is equal to 4.0, and take a look at the units. Meters over seconds squared. Units always work out. So now that we know a, we can sub a into both of these equations if need be, but it's only asking for during the first 5 seconds of motion. So we're only going to sub it into equation 1. So we're going to sub a is equal to 4.0 meters per second into equation number 1. So d1 is equal to 1/2 of 4.0 meters per second squared times 5 seconds squared. 5 squared is 25. 25 times 4 is 100. 100 divided by 2 gives you 50 meters. So if you go back to the graph that I accidentally deleted, during the first 5 seconds, you traveled 50 meters. After an additional 5 more seconds, or at the 10-second mark, you'd add another 150 meters there. And if you try doing the math, you'll probably end up getting 200 for the second equation. The 4 seconds into a over here, you'll mathematically get your 200 meters. And 200 meters minus 50 will give you your 150. Question number 14 is one where, again, it's nice to draw a diagram. So, cop car is stationary, sees a speeding car traveling at 100 kilometers per hour, and eventually the cop car wants to accelerate so that they both meet at the same position. And the question is, how long does it take? And at what distance will they meet each other? So in other words, we're going to create 2 equations, one equation to represent the speeder, another equation to represent the cop car. And as you may know, with 2 equations with 2 unknowns, what do? Exactly, you sub and solve. So we'll do that. We start off with our equation number 3, because that will help us out here. Delta d is equal to vi delta t plus 1/2 a delta t squared. Delta d has the same meaning as df minus di is equal to vi delta t plus 1/2 a delta t squared. So df is equal to our initial position plus our initial velocity times time plus 1/2 uniform acceleration times time squared. Again, they're both starting from the same exact position between the speeder and the cop car. So we know that di goes to 0. And beyond that, each person or each vehicle takes on a slightly different equation. As for the speeder, we'll just call him ds. That's equal to v delta t, as the speeder is just maintaining a constant speed and has no acceleration. As for the cop car, we have dc is equal to, well, since the cop car started from rest, our vi goes to 0, but we have 1/2 acceleration of the cop car times time squared. And we know that the 2 times will be exactly the same at the end of the day, and the positions will be the same at the end. All right, let's just sub in what we know, and we'll continue from there. ds is equal to the speeding cop car of 100 kilometers per hour divided by 3.6. You end up getting 27.78 meters per second, delta t. So that's equation number 1. Equation number 2 is equal to 1/2 times 3.6 meters per second squared, delta t squared. So since ds is equal to dc, we equate them together. So 27.78 meters per second delta t is equal to 1/2 of 3.6, which is 1.8 meters per second squared, delta t squared. Delta t squared Now, when we bring all the terms over, we get 0 is equal to 27.78 meters per second. Delta t, bring the other side over, will be minus 1.8 meters per second squared, delta t squared. So in this case, we'll factor out the delta t. So delta t is equal to 27.78 minus 1.8 delta t. We can see our two roots. One of them is t is equal to 0. And the other one is t is equal to 27.78 divided by 1.8, which is 15.43 seconds. Those are our two roots. So we have two valid answers. Delta t is equal to 0 or 15 seconds. Why is that? Well, take a look at the diagram again. Isn't it true that they were both in the same position at the beginning? And at some point, 15 seconds down the road, they both meet up again. The second part of the story is, well, where did they meet up? So what do? Well, you sub it into one of the two equations that I erased. I'll do the first one because it's a lot easier to write out. Delta of the speeder is equal to 27.78 meters per second times delta t. So 27.78 meters per second times, again, don't just leave it at 15. You want to carry at least one extra significant digit. 2 extra is a bit more ideal. And then when you crunch it out, you end up getting 428.64 meters. Taking a look at your givens, worst case scenario is 2 sig fig, so that will round to 430 meters. Unfortunately, 430 meters is ambiguous. It could either be 2 sig fig or 3 sig fig. So just for clarity's sake, we'll convert it into scientific notation of 4.3 times 10 to the 2 meters, and that's guaranteed to tell the reader they meet up at roughly 430 meters. You could also argue that 0.43 kilometers is also a valid answer, as it is still 2 sig fig. As for part C, what is so weird about this? Well, if we take a look at the velocity of the cop car at the end, so we use this equation, Vf is equal to Vi plus A delta t. Initially, the cop car starts from rest, but then it starts to uniformly accelerate at 3.6 meters per second squared. And it does this for quite a bit of time, a duration of 15 seconds, or 15.43 seconds. And when we crunch through this, it works out to roughly 56 meters per second, which again, to you and me doesn't mean much, but if you multiply this by 3.6, that works out to 200 kilometers per hour. And when you look at this number, that's pretty insane.